Hello, everybody. Welcome to this webinar 2, where Professor Adisa Azapagic will talk about understanding the life cycle implications of the circular economy. And after the presentation, there will be time for question answer. During the question answer, we will also start a poll to get your opinion on the webinar. So please also fill out that questionnaire. It should be very simple and easy, but we'll tell you when it is started. So let me start by introducing Professor Azapagic. Professor Azapagic is MBE, FR Eng, and also Professor of Sustainable Chemical Engineering at the University of Manchester, where she leads the Sustainable Industrial Systems Group. She specializes in sustainable production and consumption, helping industry, policymakers, and other stakeholders to identify and implement sustainable solutions to currently sustainability challenges. She has over 200 publications in the field, including 3 books. Also, Professor Azapagic is the founding editor-in-chief of Sustainable Production and Consumption Journal. With that short introduction, I invite Professor Azapagic to start her presentation. I will stop the screen share so you can share your screen.
Good morning, and thank you very much for this introduction. I'm very pleased to be able to speak to you this morning about this topic, and thank you for taking the time to attend the webinar. So the topic of the webinar is the circular economy, and I'm going to focus on how we can understand the life cycle implications of the circular economy approach. So here is the overview of my talk. I'll start with an introduction. Then I'll say a few words about the need for the systems approach and life cycle thinking when we are talking about the circular economy. I'll also talk about the circularity versus sustainability concepts, and I'll illustrate all of that on 3 examples. One is related to food waste, another to domestic appliances, and the third one to takeaway food containers. Then I'll draw some conclusions, and then hopefully we can have some interesting Q&A session. So let me start with the basics. The circular economy concept. I'm sure you will be familiar with this, but it doesn't harm to remind ourselves. According to the definition used most widely and put forward by the Ellen MacArthur Foundation, the circular economy should be regenerative and restorative by design. We should keep products and resources in use as long as possible. We should extract the maximum value of products and materials while they're in use. And we should eventually recover and regenerate products and resources at the end of life. So contrary to popular belief, circular economy isn't just about recycling. It is much broader than that, and it involves many other steps before we come to the point of recycling. So here is the famous so-called butterfly diagram, which illustrates the circular economy concept. Again, this is the Ellen MacArthur Foundation. So let's analyze this butterfly diagram. So in the middle, we have the spine, which follows the life cycle of a product. So it starts from the manufacturing of parts and then goes on to the manufacturing of products and then provision of service by those products. And then it splits into two wings. The left-hand side wing is all about regeneration. So you can see on top of the slide on the left-hand side, it says regenerative. So that's the regenerative part of the circular economy. And on the right-hand side, or right-hand side wing, we have the restorative part of the circular economy. So what does it mean? In the regenerative part, we can see that at the end of life of a product, we collect it, and then we try to extract biochemical feedstock, for example, and then we can go through a number of cascades. Then after that, we can try to recover some energy by anaerobically digesting biological waste, if that is possible. And then we can continue in that cycle. Maybe we can use that the product of the anaerobic digestion as a fertilizer for farming. And then maybe eventually the outputs will come back into the main life cycle or the beginning of the life cycle of another product. So this is all about regeneration. If we look on the right-hand side of this diagram, this is all about restoring products and materials. So at the end of life, once we've collected the product, we can maintain it and keep using it. So we repair it, or we can reuse it and redistribute it, or eventually we can refurbish it, remanufacture it, and recycle it. And maybe some of that goes to the beginning of the life cycle, maybe some of that goes to the middle of the life cycle, and so on. So the whole idea is really to keep materials and products circulating in the economy as long as we can. The last options here, you can see at the bottom of this diagram, is energy recovery and landfilling. So we should, according to this the principles of the circular economy, we should really not landfill, and energy recovery is just one of the last options. Intuitively, one could think, well, this is good, isn't it? And it makes sense. However, we don't really know, do we, before we put some numbers to it. And as engineers and scientists, our first instinct is to check any theoretical claims. So my postulate here is that if we are to understand truly the implications of the circular economy for the sustainability, we ought to understand, we ought to take a systems approach and adopt life cycle thinking to understand and quantify what options are better. Should we go for the regenerative or restorative, or maybe some other options are better? So how can the systems approach and life cycle thinking help us in that? So what we see on this diagram here is a life cycle of a product. So we start from the extraction of raw materials, then the manufacturing into a product, then that product is distributed to the user, and then eventually that product reaches the end of its lifetime. It can be recycled, or it eventually ends up in a landfill. So within this life cycle, as I've shown earlier, we can have various circular economy options. But unfortunately, none of that comes for free. So either in the original life cycle or subsequent life cycles, or any of these options in the circular economy, we are going to use some resources and we are going to generate environmental impacts. We are going to incur some economic costs as well as social impacts, but hopefully we are going to generate some economic and social benefits. Now, taking this approach and understanding all these aspects of sustainability and quantifying them can help us to understand which of the circular economy options we should go for in particular circumstances. And this is what I would like to illustrate through those three examples that I mentioned at the beginning of my talk. And I'm going to start from the last postulate of the circular economy, and that is to recover and regenerate products and resources at the end of life. And we are going to follow that regenerative part of the circular economy cycle. And so this is where we are. So we will be on the left side wing, and we are going to, in particular, focus on anaerobic digestion and recovery of energy and fertilizers for the agriculture. And the example that we will talk about is food waste, something that we are all familiar with as consumers, but also as scientists and engineers, and something that is omnipresent on the planet. And the question that I'm going to ask is, should we digest, compost, or perhaps burn, or even bury food waste? So applying a systems approach and life cycle thinking and using life cycle assessment as a tool to quantify the environmental impacts of food waste management, this is what we get. So here are the four options that we can consider for food waste. One is anaerobic digestion. Another one is in-vessel composting. And then the other two are incineration and landfill. So incineration and landfill are unfortunately still prevalent options in many countries in the world. Anaerobic digestion is getting traction in some regions in the world, and in-vessel composting is perhaps lagging behind. So all these four options recover some useful products. Anaerobic digestion recovers electricity and fertilizers. In-vessel composting recovers compost, again, which can be used in agriculture. Incineration can recover electricity and heat. I'm going just for simplicity to focus on electricity. And landfilling of food waste can also recover electricity and heat through the landfill gas, biogas. But again, I'm just going to focus on electricity. So all of this will require some resources and will generate some environmental impacts. I should mention that in my talk today, I'm going to focus on environmental impacts only. So I'm just going to consider the environmental dimension of sustainability. But of course, similar analysis should apply to the economic and social sustainability. So if we quantify the environmental impacts through life cycle assessment of these four options, here is just an illustration of what we get. So this graph shows a selection of life cycle impacts, such as the carbon footprint or the global warming potential, acidification, eutrophication, and various types of toxicities, human toxicity, marine ecotoxicity, and particulates formation. The four options are denoted in different colors. So anaerobic digestion is orange, incineration is blue, composting is purple, and landfill is green. There is no significance to the colors, I should mention. And the graph is not to scale, so this is just for illustration purposes. So if we just look at the carbon footprint, we notice that the anaerobic digestion is the best option. And it even has a negative carbon footprint, which means it saves this much greenhouse gas emissions because of the credits it gets for the recovery of energy and fertilizer. The worst option is landfill. And the second worst option is in-vessel composting. So what we see here is that if we remember the circular economy approach, the anaerobic digestion, which is part of the regenerative cycle, is indeed the best option for the carbon footprint. But unfortunately, in-vessel composting is worse than incineration. So in this particular case, the claim that regenerating is always better than recovering just energy is simply not true in environmental terms. If we look at the other environmental impacts, for example, anaerobic digestion is much better for human toxicity and marine ecotoxicity. But then incineration is not too bad for marine ecotoxicity either, because it also has a net negative value. If we look at the particulates formation and acidification, we now see that anaerobic digestion and in-vessel composting are the worst options. Much worse than incineration and landfilling, which according to the circular economy principles we should avoid. So what do we draw out from this example? We see that in-vessel composting is the worst option for most impacts. So in this case, circular does not translate into at least environmentally sustainable. We don't know about the economically and socially because we are not looking at that at the moment. Anaerobic digestion is the best option for the carbon footprint and most other impacts. So for this, we could say broadly the circular economy principles apply. However, it's not true across all the impacts because it has much higher acidification and particulates formation, particularly PM10s. Now, if we again take a systems approach and step back and forget about circular economy and look at the consumption, we see that much greater benefits would be achieved through waste prevention. In fact, several orders of magnitude. So if we can all collectively waste food less, both through production and consumption, then we would achieve much more in across the dimensions of sustainability, rather than applying the principles of the circular economy. And even if we apply the principles of the circular economy, we see that we don't necessarily gain that much in the environmental terms. So this is an illustration how we can use quantitative analysis to test the theoretical principles of the circular economy. Let me now move on to the next example. And I'm going to talk about regenerative and restorative by design approach. And here I'm going to choose, so this is on the right-hand side of the butterfly diagram, as shown by this red circle. So I'm going to choose perhaps an unusual example for this audience, but it's an example which I find quite fascinating, and I should hope that we are all familiar with the vacuum cleaner as consumers at your home. So what's so fascinating about vacuum cleaners? Well, to start with, 200 million vacuum cleaners are in use in the EU alone. I don't have the world figure. And 45 million new vacuum cleaners are sold annually. Now, what's also interesting is to look at what are the annual impacts in the European Union from producing and using these vacuum cleaners. And here are some figures for you, again, carrying out a life cycle assessment. We find out that 11 million tons are emitted of greenhouse gases per year from vacuum cleaners. 31 tons of resources are depleted per year. And then various other impacts go into kilotons, megatons, and so on. So the numbers are huge. But this is not why I want to talk to you about vacuum cleaners. I want to focus on two aspects. One of those aspects is that some time ago, a directive was adopted, which is called Eco-Design Directive, and it targets high energy consumption devices, domestic appliances, and the aim is to improve energy efficiency. And that directive alone has been quite successful. So the energy efficiency of vacuum cleaners has been improved simply by reducing their power. And this graph shows how these impacts that I'd shown you in the previous slide have been reduced by introducing this Eco-Design Directive, which focuses on improving energy efficiency. Effectively, all the impacts have been halved. And this is really a great success story, that simply by reducing the power of vacuum cleaners, we have achieved such a significant reduction. But now the next question remains, what about the material resources that go into those vacuum cleaners? And how about their environmental impact? And what do we do with all those vacuum cleaners at the end of their life? An estimate shows that a vacuum cleaner is changed every 5 years, not because it's no longer functional, but simply because people want to change to a new model and so on and so on. I don't know if you were ever tempted to disassemble a vacuum cleaner, but this is what you get if you do. So this is what we did as part of our research. I took a typical vacuum cleaner and disassembled it. And here are the various parts that go into it. The fascinating thing about it is that we counted 150 pieces that go into a humble vacuum cleaner. And when you look at it from the disassembly and then reassembly point of view, which is what we are talking about in the circular economy, there were around 40 pieces that theoretically were not required. So you could simply get away without them. In disassembling this vacuum cleaner, we had about over 300 repetitions of various tasks. A poor person that needs to disassemble this to be able to recycle it within the circular economy. Then we counted over 100 tool manipulations to achieve that disassembly. And also we counted that the number of tasks that didn't add any value to the disassembly process was over 100. So just this tells you the massive task that lies ahead if we want to do something with the vacuum cleaners at the end of their lifetime. The other interesting thing is that it had 15 types of different materials, in total about 4.4 kilograms. 8 types of plastics alone. So this graph shows you different types of materials, and the red circles signify the types of plastic. Then the metals and so on. And one really can't stop wondering, is it really necessary to have such a variety of materials and such a variety of plastics, most of which is not recyclable? So again, when we are talking about circular economy, the question is, how do we get away from so many pieces that go into an appliance such as vacuum cleaner, and there are many others that are very similar. Just take the dishwashers, washing machines, and so on. And how do we simplify their design so that disassembly is much easier? And also, how do we minimize the number of different materials? So this has to start from the design and from the manufacturer. So here are some suggestions, again, based on our learning from this process. For example, there were many painted parts, and that, of course, reduces the recyclability. So if we can get away from painting those surfaces, then we would increase the recyclability. We should increase the recyclable materials that go into the design and manufacture. We should increase the parts with labels, because most of the parts were not even labeled. So we had to guess what they were, what materials they were. And of course, that will contribute towards the easier maintenance and remanufacturing and so on. Then there were so many different joints which were of different materials. So when you disassemble and if you want to reassemble, then it's really difficult to do that. So the number of material joints of the same material should increase. There should be more reversible joints, because if you do reversible joints, then of course it's much easier to disassemble and reassemble. So these are all really very simple suggestions, but it's mind-boggling. Why isn't anyone doing? Now, maybe this isn't quite true what I've just said, that nobody's doing it. There are many examples, and some of them are shown in this slide. Unfortunately, there are still just examples and showcases, and we still don't have it to scale where it matters. So various manufacturers have adopted different parts of the circular economy principles. So Miele, for example, produces products, vacuum cleaners that are very long lasting, over 20 years. The unfortunate thing is that the consumer doesn't like that, because people like to change. Dyson is very much into the recycling of their vacuum cleaners. So their design, one could say, is probably closer to the principles of the circular economy. Some of the producers use natural materials. If you look at the middle one here by Cambridge Consultants, the vacuum cleaner is made of, or rather the handle and some parts are made of wood. Yet another producer allows you to assemble your own vacuum cleaner. It comes packed in a cardboard box like this. And then as you open it, that becomes the body of the vacuum cleaner, and you can assemble it yourself. Or Electrolux, for example, collects plastics from the sea and creates these very colorful vacuum cleaners. But as I said, unfortunately, as good as they are, these examples are just that, examples, and we don't have that happening at a mass scale. We are talking about 200 million vacuum cleaners just in the EU. Okay, enough about vacuum cleaners. Let me move on to my next and final example. And that example is about keeping products in use as long as possible. This is another postulate of the circular economy. And I'm going to test the validity of this claim on an example that, again, you should all be familiar with. And this is single-use plastics, which we are talking a lot about and have been lately. And the question that I'm going to ask is, should we ban single-use plastics, or should we not ban it? And the example to illustrate that is takeaway food containers. So I'm going to compare single-use versus reusable containers. So let's look at the single-use containers. Again, I'm going to focus on the European Union. Between 500 and 850 million single-use containers are used annually in the European Union. And most of that ends up either being incinerated or landfilled. And the typical containers that are being used are shown here on top of this slide. On the left is the polypropylene container with the same lid. Then in the middle is the extruded polystyrene, EPS, what most people refer to as expanded polystyrene, but actually it's extruded. And the third one is the aluminum container with a cardboard top. So I'll compare these three with a reusable container known as Tupperware and made from polypropylene typically. There are glass ones as well, but they're not that common. So we'll focus on the polypropylene. Just to give you an idea about the end-of-life management of these different materials in the European Union. So polypropylene, some of that is recycled, around 11%, but the rest is incinerated and landfilled. Aluminium is recycled, about half, and the rest is landfilled. And the polystyrene is landfilled and incinerated. It's not recycled at all at present. So applying life cycle thinking and using life cycle assessment as a quantitative tool to estimate the environmental impacts of these three single-use containers, this is what we get. So on the x-axis, I'm showing a selection of environmental impacts, such as the carbon footprint, resource depletion, and so on. And the three colored bars are EPS is orange, aluminium is purple, and polypropylene is green. So if you just pause for a moment and look at this graph and follow the orange color, so EPS, you notice at a glance that EPS actually is the best option among them all across the environmental impacts. Aluminium and polypropylene vary among different impacts, but aluminium is better, for example, for the carbon footprint than polypropylene, for eutrophication, acidification, and summer smog, and polypropylene the other way around for the other impacts. So what does this tell us? Let's have a look. So the EPS has 7% to 28 times lower impact than aluminium, and about 25% to 6 times lower impact than polypropylene. What's the reason for that? It's very simple. Less material is needed, so less EPS is needed than polypropylene, because EPS is so light, and less energy is used than for aluminium, and hence EPS is a better option. You may perhaps find this surprising because there is so much negative publicity around EPS, because we see it in the environment. It ends up in our streets, in oceans, and so on. But quantitatively, from the environmental point of view, EPS is better than either aluminium or polypropylene. And that's the fact. Now, what's interesting is to compare these single-use containers with a reusable container, the one that I showed you earlier, so Tupperware polypropylene. So I'm going to compare it first with the EPS. Here is the impact that we have, that we've seen earlier, and the numbers here tell us how many uses of reusable containers are needed to equal the impacts of single-use containers. So to become equal or better than the single-use container, the reusable container must be reused 18 times for the carbon footprint. Only when you use it 19 times, it becomes better than EPS. So it has a lower impact than the EPS single-use container. For resource depletion, this goes up to 208 times. And then for the other impacts, it ranges from 16 to 37. This tells us that from a life cycle point of view, the single-use container is a much better option than a reusable container, unless you exceed the number of uses shown here. Unfortunately, often the number of uses is lower than that because they either break or people can't be bothered or haven't got a reusable container when they want to take food. For the aluminium, the situation is a little bit better simply because aluminium has higher impact than EPS. So the number of reuses of reusable container is lower. It goes down to 11 for the carbon footprint, 3 for resource depletion, and so on. So in summary, for this example, single-use, non-recyclable EPS has the lowest life cycle environmental impact. And single-use polypropylene container is the worst option for most impact. Reusable polypropylene container, as we've seen, needs to be reused many times to match the single-use EPS container. Recycling of EPS is, of course, technically possible, and there is some of that starting to happen, particularly in Japan and some other regions. But of course, it's costly. It's costly because of the logistics and collection and so on. So in this particular example, we see that circular does not translate into environmentally sustainable. But of course, debate with the plastics is a very controversial one, and it's very emotional one, because we see plastics in the environment, we see plastics in the ocean. But to my mind, that debate should be about waste management, not about banning this type of material or that type of material. The question is, well, of course, the question is always, how do we minimize use? That's a systems thinking. But once we have that waste, what do we do with that? And putting better waste management practices for plastics would solve many of the problems that we have. And plastics, of course, is a very versatile material. I'm not advocating one material or another. I'm just looking at the quantitative analysis from the environmental point of view in this case. but also from the economics and from the social point of view. So now drawing overall conclusions based on what I was talking so far, we know that most products and services are not designed for a circular economy, and we are facing a huge challenge there. We will also need to understand better when circular is sustainable, because what we are seeing now is a huge push towards circularity. But as I've demonstrated through these fairly simple but ubiquitous examples, we don't really understand when circular is sustainable. So we need to do much more research and thinking in that respect. I've also argued that the systems and life cycle approaches are essential in gaining that understanding, and I've illustrated how we can use life cycle assessment as a tool in that respect. Implementation of a circular economy will be challenging, but I believe is achievable. Drivers are increasing. We see, particularly in the European Union, legislation is going that way. There are many directives stipulating the implementation of a circular economy. Methods and evaluation tools are becoming more available. Life cycle assessment is just one of those, but there are many in process systems engineering. Of course, there are many design tools that we can use, combined with life cycle assessment and others. And technologies are developing to help this transition towards a circular economy, albeit very slowly. We also need more success stories to stimulate the uptake of a circular economy when that makes sense. And I also believe that voluntary actions are all very well, but legislation will need to get tougher. This is already happening in the European Union, but I think this needs to be spread in other regions as well. And finally, I would like to acknowledge some members of my group who have contributed to this work over the years, and to the funding from the research councils in the UK. And that concludes my talk for today, and I'm now happy to take any questions, if there are any. Thank you.
Thank you, Professor Azapagic, for an excellent lecture. The question answer will begin very soon. Before that, the hosts from Thailand, they will inform you about a poll that they will start, and then we will start the question answer.
Okay.
So, Orakoch, can you explain?
Yes, we will have some question to get your feedback for our future organization for the webinars. So any comments from your will be very benefit for us. Okay.
So you will see this poll and please answer the poll so we can improve the webinars in future. With respect to questions, we will take questions. If you show your hand, we will take them. And also you can put your questions on the chat, and I will read out the question and Professor Azapagic will answer them. So I can already see that there are 2 questions on the chat, and I will read them out. First is from Yogendra Shastri, and he is asking, is the study on food containers published?
Yes, it's published, and I have put let me just go back to that slide. I've put the publication at the bottom of each slide. So if you look here, it's in Journal of Cleaner Production, 2018, volume 211.
Okay, so another question on the chat is from Ifat Sherbin, and she is asking, can you please explain the cascades between the feedstock extraction and the collection stage of the butterfly diagram? And is it reasonable to generate electricity from landfill?
Sorry, I just
Shall I
went
read
to
it
the
out
diagram.
again?
Yeah, I'll go back to the diagram and then I'll put it in the presentation mode. So you want me to explain the cascades from the extraction of biochemical feedstock? Was that the first part of the question?
Yes, it said, explain the cascade between the feedstock extraction and the collection stage of the butterfly diagram.
Yes, so the idea here is whenever we collect the product from the first life cycle, that perhaps if it's a biological in nature, of course, that we try to extract a feedstock, a biochemical feedstock from it through manipulation. And then if that's successful, we can go back into making into a consumer and circulating it before we attempt anything else. So that's what the idea here is in terms of cascading the use of the product at the end of its life cycle. And I think the second question was, is it reasonable to generate
electricity from landfill?
Yes, it's very reasonable. It's happening in practice in many landfills. Yeah, so it's common practice because, well, at least in the European Union, the landfill gas must be captured, and then many landfills generate electricity and draw income from that because they export it to the grid.
Okay, the next question is from Tom Rongrut. I will not try to tell the full name. The question or comment is, circular economy is gaining more popularity due to the economic point of view. So comprehensive sustainability aspects like economic, social, environmental should be illustrated, not just the environmental sustainability.
I couldn't agree more. That's exactly what I was saying throughout my talk. I focused on the environmental sustainability due to time constraints, but as I said in the talk, a similar type of analysis applies for the economic. So we should use life cycle costing, for example, to check the validity of the claims, as well as social sustainability. So we should understand, for example, what is socially acceptable and what isn't. And often we will find that there is conflict between the environmental, economic, and social aspects. And then we as a society need to decide how we deal with that conflict and what trade-offs we are prepared to accept. Maybe
before another question comes, I can just add one question on this discussion. Doing this kind of sustainability analysis myself, I found the environmental sustainability and the economic to be more easier to do because the data are more easily available, whereas the social becomes very difficult because of the data and the uncertainty in the data. Yes, absolutely. And again, for us as scientists and engineers, we are more familiar with the economic and environmental types of analysis.
whilst we somehow leave the social assessment to social scientists. I agree. It's more difficult, not just for us, but it's even difficult for social scientists because you often get conflicting messages from consumers, depending on what groups you ask and what questions you ask them. But nevertheless, it's really important to get more insights into that, gather more data, and get tools developed. For example, we have social life cycle assessment, which helps towards that. But unfortunately, it's so complex to carry it out, and it's very data hungry. And as you say, we don't really have those data. So it's an ongoing research need.
Okay, there is another question also from Yogendra Shastri, who's asking, are the concepts of circular economy and cradle to cradle in LCA related?
Yes, certainly they are related. So cradle to cradle means going back to where it all came from. And the circular economy is advocating that sort of approach. So yes, they are related. I think there was a second part of that question, but I can't see it. It says if yes.
Yeah, I also, it's just said if yes. If you want to ask your question, Yogendra Shastri, you can raise your hand and then they will unmute you to ask your question, or anybody else.
Yeah, I think I could unmute myself.
Okay.
Can you hear me? Yeah, sorry.
Yes.
So I just wanted to know if they are related, then they are, what is the connection? So I think you have already answered that question.
Okay, thank you.
Thank you.
Is there any other questions? I do have one question before others can ask then. Going back to the butterfly diagram, and as you also said that to implement circular economy, we have to try to implement circular economy, but from the examples, it looks like what we can implement is a sustainable circular economy, but not the circular economy showed in the butterfly diagram. And if I take just one example of the recycle, thermodynamics say that 100% recycle is not possible, but we could always replace one product with another or one resource with another to continue the service, but the product or the resource will ultimately end. So any comments on that?
Yes, I mean, obviously from the thermodynamic point of view, we can't 100% recycle. The question is always what alternative is better? Is it better to keep recycling, or is it better to simply replace one product with another? And that's exactly the type of questions that I would like us to be asking all the time. And the answers may be different for different products. In some cases, it may be better to continue recycling as long as we can. But in others, it may be better to simply replace it and not even attempt to recycle. But the challenge is because we can't answer these questions in general. It doesn't apply.
Yes, but on the butterfly diagram, I didn't see a replace, because a replace would actually continue the service continuously, let's say, whereas recycle is not possible.
Yeah, you're right. It doesn't say explicitly replace, but I think that trying to get away from that concept of, consuming more, and they're trying to keep products and materials in the loop as long as possible. That's the kind of idea.
Yes, but that's why I think maybe we should say sustainable circular economy rather than just circular economy.
Yes, if we are sure that it's sustainable circular economy.
Okay. Are there more questions? There is one more comment. No. So, well, then I would say, again, thank you very much, Professor Azapagic, for a very interesting lecture. Very interesting to know some aspects of circular economy and sustainability that were new to me also. So it was very interesting. And for those who are attending, I hope you answered the poll so we can also improve our future webinars. The next webinar is on August 10 on process design. What should be the best way to teach process design and what should be the contents of process design? And of course, sustainability and life cycle assessment is also part of it. This will be given by Professor Danny Levin and Warren Cedar, and there will be a panel of 4 experts who teach process design, who will also be commenting on the webinar. It will be a longer session. It will be a 3-hour session, but please do register and join, and it will be the let's say the joining of the webinar will be based on a first come, first serve, because we have upper limit of how many people we will allow. So do make sure to join because we are already oversold. And with that, I thank again Professor Azapagic and thank you all the participants for attending. I hope it was useful for you. And wherever you are, good day, good night, good evening. Thank you very much.
And thank you from me too. Thank you, Rafik, for inviting me, and thank you to the attendees for listening. Goodbye now.